Okay, anyways, okay, so let's start the Wednesday session. So we're very fortunate to have Ryan from CMU, who I would say is the world leader in applying stat solving and solver methods to problems in mathematics. So he'll tell us about some of his recent work and maybe a half an hour. Then we'll discuss some of the problems that we came up with on Monday and see if this might be a fruitful approach. Segues with general compares machine learning and stat solving and other approaches. Thanks.
Okay, thanks, Mike, for the invitation. So what I'm going to talk about is a problem that has been open for almost a century that was solved with symbolic AI, or more specifically, satisfiability solvers. And this is joint work with Manfred Scheuze. So what I'm going to talk about is problems that are around point sets, so points in the plane in general position, meaning that there cannot be 3 points in a line. So throughout this talk, I'm talking about point set, and all of them holds no 3 points in a line. The focus here is on the so-called empty hexagon, which is a 6-hole. And what is a 6-hole or a k-hole in general? A k-hole is k points in convex position without a point inside. So on the left of the slide, I show you 7 points and the same 7 points on the right. And there is a 5-hole, what you can see over there on the left, but there is not a 6-hole because the 6 points are in convex position, but there is a point inside. And the problem asks, okay, what's the fewest number of points that you need that no matter how you place them in the plane, you always have a k-hole for some k. Right? And so but even the question is whether that actually whether the number of points is finite. So is it the case that for sufficiently large point set, it always is the case that you have a k-hole? And if it will be there eventually, then you are also interested in what is the exact point where it needs to happen. So as I mentioned, this problem dates back to the 1930s. Of course, with 3 points, it's trivial, right? As soon as you put 3 points in the plane, and you cannot put 3 points in a line, then if you put 3 points in there, then there are 3 points in convex position without the point inside. Slightly more complicated, but I will show you a very nice short proof of that in the upcoming slides, is that if you have 5 points in the plane, you always have a 4-hole. And this was actually the proof that I'm going to show you is the one by Klein. Then it took a long time before there were more results in this area, because it took until 1978 to show that you need 10 points in the plane to have a empty pentagon. And maybe a more kind of surprising result is by Horton from 1983, is that you can have arbitrary large point sets in the plane without a 7-hole. And so the result of, say, 50 years of research in this direction is that we know all of the values except for the empty hexagon. And for a very long time, it was unclear whether it was the same case as 7, as that it would be infinite, or that it would be finite. And in 2007, 2008, there was a proof, 2 independent proofs showing that it is finite, but a large number. And the conjecture was that it is 30, and that is actually what we showed using SAT solvers. So if you have 30 points in the plane, you have an empty hexagon. Now let's talk about the the 4-hole situation. So it's kind of clear that if you put 4 points, so you have a triangle and you put a point inside, then you have 4 points and there is not an empty 4 gone, right? So you need at least 5 points to have a 4-hole. Now let's look at Klein's proof of every set of 5 points has a 4-hole. So I consider 3 cases. One condition is that the 5 points are in convex position. In that case, it's trivial. You drop one of the points and you have an empty 4-hole. You have your 4-hole. Another point, the next option is that you have 4 points in the outer hole is 4 points, and so there's 1 point inside. What you then do is you draw both diagonals, and the point needs to be somewhere because it cannot be on one of the lines because there cannot be 3 points on the line. And you simply drop one of the points that is in the quadrant, in the quadrant of the point that you have. And so you drop, for example, either the lowest point or the highest point in this case to end up with a 4-gone or 4-hole. And the third case is the outer hole is 3 points, and so there are 2 points in the middle. Then we take a line through the 2 points. It always needs to be the case that there are 2 points on one side of the line, and we just take the 2 points on one side of the line and the 2 points in the center to have our 4. Is that clear? Yeah? Okay.
Which Klein was it?
Sorry?
Which Klein?
Esther Klein.
Thank you.
And she married with Semmerady.
Huh.
And actually, because of this, they were both worked with Paul Erdos, and since their collaborative work resulted in their wedding, Erdos named it the happy ending problem. Now let's look at the case for 5 holes, so the empty pentagons. There you can have 9 points as shown on the slide. You have 9 points that all of the pentagons that you can make. For example, there's a pentagon over here. They all have a point inside. And it's a bigger case split to show that you have 10 points, right? So it's actually it took quite some time to actually compute it. Although we now have some smaller proofs, but they are too large for kind of this talk. In 2002, Mark Overmars proved that showed that there are 29 points in the plane without a 6-hole. So that gave us the lower bound of 30 points. And he found it using simulated annealing, using months of computation. And if you use the same approach that I'm going to talk about now, then you can use it in a second. You can use SAT solvers to get a very similar set of points. Interesting, it contains several 7-gons. So these are 7 points in convex position, but with points inside. And another interesting result is that each 9-gon contains a 6-hole. And that's actually how they proved that the 6-hole problem is finite. Let me talk a few brief words on that 7 holes can always be avoided. This is this Horton construction, is you take a set of points that it doesn't have a 7-hole, and what you can do is you can make a copy, move it upwards, shift it slightly, and you can do this always in such a way that you do not create a new 7-hole. And you just repeat this procedure. Actually, Horton gave concrete coordinates how to do this, that you can always avoid a 7 hole. Now, okay, we want to solve this problem using SAT, but if you want to put points in the plane, right, you think, okay, do I need to use reals? How am I going to encode reals? This is not what we're going to do. What we're instead going to do is we're only talk about the relationship between points. And so what we're going to do is we have Boolean variables for each triple of points, A, B, C. And so where we have A left of B, B left of C, what we're going to do is if you would draw a line through A and B, then is C either above the line AB or below the line AB. Right? And so we have propositional variables O, A, B, C, and if it's positive or 1, then the C is above the line, and in this case D is below the line, so the variable A, B, D would be false or negative. And the nice thing is that these triple orientations, so these variables are enough to kind of express whether we have pentagons and hexagons with or without holes. And I will talk a bit about it later on, but without loss of generality, we can assume that if for the point sets we're looking for, that the points are sorted from left to right. An interesting thing here is that not all point sets are realizable, or assignments to those variables are realizable. Realizability is actually a very hard problem, but with some additional clauses, which I also talk about later, we can eliminate many of the unrealizable assignments. Now, this will get a little bit of technical. Please let me know if there's any questions. So what we're going to do is, so we have these variables O, A, B, C, stating that if you draw a line through it, A, B, whether C is above or below the line. Additionally, we need variables to say, is a point within a triangle ABC? Is a point X in between a triangle ABC? And so we have these variables I, X, A, B, C. There are kind of 4 cases here. Either C, depending whether C is above the line AB or C is below the line AB, and whether X is in between A and B or whether X is in between B and C. And so let's look at the possible case over here. So if X is in between A and B and C is above the line AB, then the only thing to make sure to ensure that X is in between ABC is that X is above the line AB and X is below the line AC, which we can again express with these O, ABC or OXC variables. Right, we don't need the other one because we know in this case that X is in between A and B. And so, and the slides also showed you the other cases here. So I want to keep this a short talk, but I just want to kind of show with some simple propositional logic, you can just express the figures shown on the slide. Now, mathematicians actually tried to solve this problem using SAT for about a decade, but they were not able to do it. And one of the reasons is that their encoding was relatively simple. What they did is that the following. They also introduced whole variables. So A, B, C forms a whole. So these are 3 points without a point inside. So if no point is inside ABC, then ABC is a whole. And in order to say you avoid a whole is that for every 6 points in the plane, you say that one of them is not a whole. If one of them is not a whole, for every 6 points, then you don't have any empty hexagons. So this is the encoding that mathematicians have been using, but that encoding is actually pretty hard for SAT solvers. And one of the contributions in this work was that we actually came up with an encoding that is much easier for the solver. So let me try to get, so how many people have been following it so far? Because I also, yeah, okay, perfect. So what we're instead going to do is that, so if we have 6 points, right, then there are these 20 literals that if you do the encoding, so there's 20 subsets of 3. But what we can do is that, say we have the points shown on the slide, A, B, C, D, E, F. And if we know that, in this case, we know A is the leftmost point, F is the rightmost point, and if we know that D is below the line AB, and F is below the line BD, and E is above the line AC, and F is above the line CE, then we know we have a hexagon. So with just 4 variables assigned, we know we have a hexagon. The question is now, okay, how can we make sure that the hexagon is empty? But so the encoding mathematicians required 20 literals, and at least we can, with 4 literals, we can make sure that we know that we have a hexagon. Now the question is, how many triangles do we need to know that to be empty in order to conclude that we have somewhere an empty hexagon? Anyone in the room? How many triangles for which we need to be sure that they are empty to make sure that there is an empty hexagon here or elsewhere?
We think 4.
You think 4. Yeah, so this is also what I initially thought, but the answer is 1. And so that's as follows. So if we know that the ADE triangle is empty, right, then we know that there exists an empty hexagon. It might not be the one over here, shown here, but if there is a point in between, somewhere in the triangle ABD, for example, there's a point here, then we can take that point and we have a more tighter 6 points in convex position, which forms an empty hexagon. And so, and it holds also for the triangle over here and the triangle over here, that there's always a point closest to the line AD, always a point closest to the line DE, and always a closest point to the line AE, and we just take those points to have our empty hexagon. So instead of using 20 literals to make sure we have an empty hexagon, we actually can do it with just 5. 4 to ensure we have the convex position of 6 points, and 1 to have the empty hexagon, the empty triangle in the middle. And this makes the reasoning for the solver so much more efficient. Right? And so in order to prevent the empty hexagon shown on the slide, we just have the negation of the assignments I show above it. So either this one needs to be true, this one needs to be true, this literal, so ACE needs to be, so false, this needs to be false, or this triangle needs to be non-empty. Right? And so with just 5 literals instead of 20, you can really speed up the search. So this encoding is 5 times larger in file size, but way easier to solve because there's much more propagation and reasoning that can be done. This is probably the most technical slide. Let me briefly, how much time do I? I don't have too much time. So I'm going to skip over this. But there are some additional tricks that we did to make sure that the encoding actually went from n to the power 6 clauses to n to the power 4 clauses. This is kind of tricky. And I'm looking into more and more options to also automate this so that the users don't have to do this, but this will be done by the solver or some other pre-processing tool. Maybe one thing to mention here, which is also crucial, is that one nice thing that we can do is that we can assume without loss of generality that the points are sorted from left to right. But additionally, and this is somewhat surprising, additionally, we can assume that all the points are sorted counterclockwise around the leftmost point. And this is kind of an unexpected thing, because that really makes the search space much smaller. The reasoning is as follows. So say we have our points, and so of course without loss of generality we can always move everything in such a way that the leftmost point is in the origin. Then what we can do is we can stretch the points to the right without kind of changing the shapes. So we stretch them, but the pentagons and sexagons will still be there in such a way that all the points are within the lines y equals x and y equals minus x. Then what we can do is we can rotate them such that all the points are in the positive x and y quadrant. And then we have this projective transformation shown over here. And that projective transformation also preserves shapes. And if you do this projective transformation, then we have both that points are sorted from left to right, and we have it that the points are sorted counterclockwise around the first point. And this was a very important symmetry breaking to get it all working. Then there we also have additional clauses to make sure that unrealizable assignments are blocked. So these are all clauses of length 3. I don't have really time to go over it, but this was also a key thing to get things working. Let me briefly talk about some experiments. So for a small subproblem, we tested the encodings, and for example, the encoding that was used by the mathematicians that used 240 seconds on this very small problem, while the optimizations I showed you here is 40 seconds, but this gap will grow and grow for bigger problems. Another thing is because the runtime was a couple of CPU years, what we need to do is we need to split the problem into multiple subproblems such that we can run them all in parallel. It turned out that the variables O, A plus 1, A plus B, plus O, A plus 1, A plus 2 are very good splitting variables. And we tested this on some other problem. And not only was it able to really split the problem such that we can run them in parallel, but even on this small problem, although small, it was not that small because it's 1,000 CPU hours. But if we split it into 7,400 subproblems, then we actually got the total runtime down to 230 hours. So it was already 4 times faster than if you just sum up all the runtimes compared to running it sequentially. So the total runtime for the empty hexagon problem was 2 CPU years, which was run on AWS. We had a linear time speed up with 1,000 machines, and the proof is 180 terabytes in the LRAD format, and we validated it also using a formally verified checker, so we can have high confidence in the correctness of this. Moreover, we constructed a kind of a proof of all the aspects here, but some students at CMU also verified in the lean fear improver the encoding that I just described, although not in too much detail here, but everything. So we have a formalization of the problem, and everything up till the encoding and the solver output has been checked in lean. And the paper was actually presented yesterday at ITP. So SAT has been an excellent kind of tool also for these kind of problems, which I really didn't think about. Okay, SAT can be used for kind of this computational geometry problems, but it seems to be the most effective technology that we have. And this opens up for lots of other problems in this area. And I have 2 additional slides here. For example, what is the minimum number of 4 GANs, 5 GANs, and 6 GANs in the plane? And another very interesting problem is the set of the problem regarding unbalanced configurations. And let me continue with that now. So the problem that we're now going to consider is somewhat related. So we're putting points in the plane, but now we are allowed to have 3 points in the line. So there's no restrictions in where we place the points in the plane. And what we want is that the point set is unbalanced. What does that mean? Is that anyway we draw a line through at least 2 points, for all of those lines, it must be the case that the difference between the points on the left and the right of that line is at least k. And so the points that you see here on the slide is the smallest example for, so it's 12 points, the smallest example for k equals 2. So and at least at least 2. So the interesting thing is it is conjectured that for every k there is a point set, such that if you draw a line for at least 2 points, the difference between left and right is at least k. But nobody was able to find any example for k equals 3. So this is the smallest example for k equals 2. So the conjecture is it holds for every k, but nobody was able to actually find it for k equals 3, let alone for anything bigger than 3. So I think there's I'm hopeful that SAT might be the best method, but I'm also really curious to any other methods to kind of tackle this problem. And this might also be something interesting to consider. The final problem that we also looked into is what is the fewest number of pentagons? So we have been regardless of whether there are points inside or not, what is the fewest number? And so we run a lot of these benchmarks using SAT and then visualize the point sets. And the interesting thing is that there were always 2 constructions coming out, either the kind of the one on the left or the one on the right. And we actually have now proven up till n equals 18 that the constructions that you're seeing on the left and the right, that they are optimal. And we conjecture that they are optimal for every n. But yeah, so far we have only able to kind of push it to 18. But there is strong evidence that this is optimal in general, and we actually offer a $500 for every proof or disproof of this conjecture.
These are all pentagons or convex pentagons.
Oh, convex pentagons, yeah. And so, for example, over here, right, the only pentagons that you can make are with the points, say all the combination of points in the lower half, or only with points in the upper half. You cannot make a pentagon, a convex pentagon, by picking some points from the bottom and some from the top. So this concludes my talk, and one of the things why I wanted to do this talk is also because I think there is a lot of opportunity also for machine learning and symbolic AI to tackle these problems in computational geometry. These problems have been open for a long time, and there have been very interesting conjectures, but limited progress. And I really think that automated methods might can make a dent here. So I think it would be cool to consider them.
We have a problem list with the status of lots of problems.
Sorry.
Is there like a list of problems of this type with the present status someplace?
I think so. My co-author Manfred, he has I think quite a list of open problems. Yeah, here.
Okay, of course we would love to see that and disseminate it.
Yeah, yeah. So I think the two problems I just showed here, I think, are the which I consider myself the more interesting ones. But there is a long list of problems that is open in this area.
Yeah, great. Okay, so now it can be kind of open-ended. We could discuss machine learning ways to work on these problems. We could discuss our problems. I'm curious to hear if there's something useful to say to compare the no isosceles triangle problem, which has been studied with both approaches, and seems to look, machine learning seems to look well for large instances of that. Is that showing that, I mean, what do we learn anything from that, or is there some way of combining the approaches? We have a couple of other problems which maybe can be phrased in a sad. So,
yeah, so that problem is interesting. So I've been also kind of competing somewhat with Adam on this. So far he was able to get somewhat better constructions. I didn't spend too much time on it, but I do think that in order to make sure that the SAT approach works well, you probably need to guide it a little bit, right? As we've seen for these problems, that the center tends to be empty. And I think that is one of the things that you probably want to tell the solver. And so this is something the machine learning probably learns, right? That, okay, the best ones have an empty center. And I guess that in order kind of for SAT to kind of find similar good results, you kind of need to kind of force the center to be empty as well. But it is an interesting problem where kind of both approaches seem to do reasonably well, and kind of in a are kind of competitive.
It's very open-ended, no question of possible hybrid approaches where I mean, there are all sorts of possibilities, I suppose. I mean, for that problem, one would come to mind would be to partially generate the configuration with machine learning and try to fill it in the SAT solver.
Yeah, no, I think that's yeah. There's a lot of potential actually of combining the techniques, right? Because their strengths are really different, right? SAT is really good into kind of exploring the entire search space, but in order to do that, it needs to be somewhat limited.
Yeah.
while machine learning has, can search much bigger spaces, but it cannot be certain that it covered everything. Yeah. And so machine learning is able to really kind of show, okay, what is an interesting region,
Yeah,
where then the SAT or symbolic approaches then can make sure that the entire search space is covered.
yeah, and that problem might be quite interesting from that point of view. I mean, is it, many of us have experience with machine learning, much more so than with SAS solvers. Is there a SAS solver one can relatively easily download and get something working, and then if the problem starts to get bigger, we can ask for professional help.
Yeah, because is Adam also in the room?
I think no.
So you may have to teach. It also takes a little while to come in the morning.
Yeah, okay. So, but then,
Recordings.
it's more that Adam and I already have been exploring some and had some discussions about how to combine the approaches, and I'm very excited about that line of research.
Right, okay, we'll talk to him about it then. So, okay, we have some other problems where I'm not sure we've given any thought to how to whether they can be usefully phrased as SAS solvent. Essentially the very concise list of problems, and then on the Zulip we have at this point more detailed explanations. So let's see. I mean, I guess you could study Kronecker coefficients as well, right? I mean, in principle, you could talk about the tensor product of symmetric group representations as a rephrase that in combinatorial terms, right? Mm-hmm. Have you worked on any problems like that with group representations, and especially the symmetric group?
Yeah, so I think one of the things that this is only remotely related was so I've been trying to find optimal matrix multiplications using
That's classic.
Yeah. So I haven't really, because the problems only came in, what was it, yesterday, or so I have not really been able to give it some serious thought yet.
Yeah. Okay, well, I mean, you can take a look. I mean, if something comes to mind, I mean, we could think about how hard is it, how many clauses do you need to express a group representation problem in terms of SAT. I mean, my initial guess would be that it would be a very large set of clauses, but maybe there's probably some work out there looking into this. So that's a thing.
Mike, but I just a quick question. So like often, in my experience with these things, like the realizability is like a real problem. And so I would imagine that, like, I'm kind of surprised in this setup that your SAT solver doesn't say, oh, here's like a zillion things, possible constructions, and then you realize that none of them are realizable.
Yeah, so that's so an interesting thing is that, because we know that only a tiny fraction is realizable of the assignments, right? Mm-hmm. But if you, for example, look at the 29 points, so the counter examples for the empty hexagon, somehow a lot of them seem to be realizable. And so the thing is that if you search for these kind of problems, then they have a certain structure. Because we are looking for a structured object. And at least in my experience, the more structure that you enforce, the more likely that it's realizable. And so we've also been looking at, for example, so you want to avoid a hexagon, so not an empty hexagon, but so it can be done with 16 points. And quite a fraction is realizable, but actually if you say something extreme, say, okay, give me the one with the fewest number of triangles that are positively oriented, or with the fewest number of foregots, then those seem to be, their fractions seem to be much likely to be realizable than random ones. And so, so far we actually have been very lucky that many of the things that we find are actually realizable. And I think the best explanation is that as soon as you enforce a lot of structure, then somehow the fraction of things that are realizable is actually high. I don't know why that is the case, but this is clearly our observation.
And so in your proof, so that, thank you, that's extremely interesting. So in your proof for the n=30 case, so you kind of get like, so it's not like you're kind of lucky in that the SAT solver doesn't suggest solutions which aren't then realizable. Is that correct?
Yeah, no, so what we, it could have been the case, right, that our abstraction on 30 points is satisfiable and that none of them are realizable. The thing is that there is no for our abstraction, there is no satisfying assignment for 30 points. So it is the case that although the search space is much bigger, because there could have been many unrealizable ones, but in fact there is no satisfying assignment at all, and so therefore also not some unrealizable ones. It could have been the case, right, is that for that the answer would be 30 and that the formula is still satisfiable up till 40, but that all of those are unrealizable. But it turned out that the point where it goes from SAT to unsat is exactly the point where it also where the original problem goes from empty hexagons doable or not doable.
Thanks.
And yeah, so this is I found it always somewhat surprising. Of course, it was not necessarily what you expect, but and additionally, what I described before, right, is that somehow the more structure you enforce by the encoding, the more likely it is that the set that things that are realizable and are not realizable kind of are almost so the things that then almost all of them seem to be realizable. And so one way, actually, in case you have a problem that is not that you find a lot of unrealizable ones, I think the best way, at least what I've seen, is actually to enforce more structure or to find a kind of extreme object within the ones that you're looking for.
I learned that principle first in your paper, Symmetry Within Solutions.
Okay, yeah.
So a general question. So we have another problem on our list of the standard chromatic polynomial positivity conjecture. Maybe you'd like to describe that a bit. But I guess the first comment looking at that leads to a general question is that that one is proving positivity of coefficients that are integers. And so I mean, there's obviously anything can be like this can be encoded in a SAT solver, but it's convenient if one's encoding variables that are 0 and 1, say. And I believe it's right that in a lot of your matrix multiplication work, look for matrices that involve zeros and ones for that reason. And then there are solvers, of course, SMT solvers like Z3 that do have some ability to talk about integer arithmetic. And it's a very open question I'm asking whether is that a direction one should also be looking in, or is the kind of the strength of those solvers so much less than a SAT solver that is kind of not necessarily the direction to look in.
So my experience here is that SMT solvers, they either solve it in a minute or they will never solve it, right? Okay. And so they have a lot of expressivity and you can easily encode something, but when it takes a long time, it typically takes forever.
Okay, so they kind of get stuck.
Yeah, and I know very few problems for which SMT solvers actually can solve it, say, between a minute and an hour.
Right.
While what you see for SAT is really that it always seems to make progress, and it actually, I have also some tools now to kind of predict kind of the runtime, which can be done reasonably accurately, and you really see there is just progress, and in the end it will be solved, although sometimes the
Well,
estimation.
that's very interesting. So this is a tool that you run, you sort of instrument the stat solver, or is it something that looks at the problem a priori and makes a prediction?
So what I do is I split the problem into millions, sometimes even billions of subproblems. And then I just do random sampling. And and that gives you a reasonably, especially if you do it a couple of times with some heuristics, a reasonably estimate how big the effort will be.
That's quite interesting. And we've already started to have a little bit of the conversation of to what extent are random results at all, like about random set or anything at all, indicative about problems that arise in mathematics, which are the interesting ones are not random. And so here's an example where you're telling us that we're applying some sort of randomness does tell you something. So
yeah, although of course there's also cases where some of the subproblems take the majority of the time, right? But you can also have some indication of, okay, so if you make a lot of them and the variance is actually small, relatively small between the runtime, then in my experience, it is the case that there hardly is a really hard one in there.
okay, well, that's makes a lot of sense, and that's very interesting. Have you tried to, I don't know, make it a little more theoretical in the sense of trying to say something about the landscape solutions?
Sorry, the sound is
So
not.
it's again kind of very open-ended question. I mean, if you were very theoretical, you might say there might be some kind of a theory of SAS solving or combinatorial optimization, where there are different kinds of landscapes, And so now you're saying here's something about the problem, again, you sample subproblems and you learn something, and that's saying something about the landscape of that problem.
Yeah, although it's all empirical, right? It's very difficult to kind of make a kind of
theoretical things, like I'm sure you like work in random stat where there's not just the main phase transition, but there's like phase transitions where things goes to percolate and solutions and so forth. Right. So like you look at the classic random 3-sat, and then there's this threshold of the number of causes to variables where below and it's all the asymptotic limit it's solvable, and above it it's not solvable. But then there are this more subtle structure of the solutions are isolated, and finding one solution tells you nothing about where the other solutions are, versus the solutions start to live in clusters and percolate and stuff like that. So there is that kind of structure that people see in the random stat.
Yeah, but my experience is that almost all problems are really different. All real problems are really different than random problems, right?
Yeah.
Some solvers are actually really bad at random problems, right? And because it's very difficult to exploit the structure, because there is actually no. Well, in these kind of problems, right, from mathematical conjectures or whether the problems come from industry, I think the strength of the solvers is actually to exploit structure, right? And also that allows you to typically also do a good split, right? Because there is structure, you might also be able to exploit the structure to split the problem in more equal parts.
For sure. I'm using the random case not to say that everything's like the random case. I'm using it sort of suggestively to say that here's a possible type of structure of the solution space, that the solutions can be isolated or connected, percolated and so forth. And that kind of statement could also make sense for a non-random problem.
Yeah, but so for example, I also I don't have a foolproof yet here, but I expect that I have almost all the solutions for 29. So all the 29 point sets that and there's millions of them that have no 6-hole, and all of them have the same structure, which is that the outer convex hull layer is 3 points, then there are 4 points inside, and then there is a layer of 7, 7, 7, 1. There is no solution of the 29 points that doesn't have the same, that doesn't have this convex hull layer structure. So, and it kind of is interesting. So here is that for random formulas, right? There are solutions everywhere pockets, but here for this problem, there's actually, if you consider only the convex hull layer structure, there's only one solution here.
So that's the structure, and then I guess I could ask, you see the structure in the space of solutions, and look at how the SAS solver found the solutions. Did it use that structure, or did it just kind of find them all and then you notice the structure?
Yeah, my experience with structures problem is that actually if the more constrained you get towards a single solution. Well, if you look at random, right? If you go to the phase transition and you just break it, you at some point you get from SAT to unsat with additional clause. If you take away that clause, the formula is extremely satisfiable with lots of solutions everywhere, right? And for structured problems, this is typically not the case. There it is the case that before the end, right, there is one solution. Although, of course, we know from, for example, Ramsey theory, right? Of course, we do not know random Ramsey number 310, but at least if it is 40, there are a lot of solutions at 40, also millions of them. And so in that case, there is not much structure there. But for most problems that I've seen, also from industry where you want to have a certain structure, there's only kind of one or some very related things, and random is completely different in that respect.
Yeah. So maybe this is an observation that the one rating now that somehow could be more precise. But is it
There's also this isosceles problem, right? It also seems to really works towards a structure that you have these points in a certain way on the boundaries. Yeah. But yeah, no, I'm also yeah. So unfortunately, I won't be able to be there in person. But I'm very happy to kind of know more about what also your ideas are from the group, how we might be able to combine
well, definitely
learning and automated reasoning.
Yeah. I don't know. Do you think it's worth talking about this chromatic positivity, or is it just too far from SAT? So,
I'm not sure. It's kind of a different.
yeah, it's certainly different on the face of it. Yeah, so maybe
There's some aspect which is kind of, I guess, there is this direct approach using supervised learning, but there is another approach which might be, possible and feasible for stuff. But I don't know. I have to think about this. Maybe I can.
Okay, we can come back to.
I'll come back to you then. Yeah. But as a direct, it's not.
So we keep going for another half an hour, so we could come back to our problems and invite off of what I mean. If you are interested in presenting Collat's, he has this other very interesting work on an approach to the Collat's conjecture, which obviously if it succeeded, we would have heard about it. It's certainly a very different technique of applying SAS solving to anything I have seen. Are people interested in that? If Marian's interested in presenting that, or should we go back to other problems? Ryan, are you willing or to give a short talk on Collat's?
Let me see. I didn't prepare that, but I have lots of slides. Yeah, so I can talk about colots. Another problem I've been really looking at, what I also really like, is the chromatic number of the plane.
Yeah, I mean, that's, okay, we can hear about that.
Yeah, what does the room want? I'm happy to talk about anything.
30
30.
Probably more similar to things we're talking about. How else it's just really different about. So maybe we do chromatic number.
Sure.
Okay, let's do that. Okay, let's do chromatic number of the plane.
Okay. Let me. Green. Okay, so what's the chromatic number of the plane? We have all the points in the two-dimensional space, and we have one constraint. If 2 points have exactly distance 1, they must have a different color. And so now the question is, how many colors do we need? Of course, it's very trivial that you need at least 3 colors, because you just have a triangle with all 3 points having distance 1 from each other. But so this problem dates back from the 1950s. And back in the day, the bounds were as follows. You need at least 4 colors. So what you see on the slide are 7 points in the plane with 11 distances 1. That has chromatic number 4. And also you see a hexagon tiling of the plane with tiles that have an outer radius slightly smaller than 1. And so all the points in the tile have the same color, but 2 tiles of the same color are more than distance 1 apart from each other. So the results from the 1950s were the lower bound 4, upper bound 7. So the first progress was in 2018 by Aubrey de Grey. He showed that a graph with 1581 vertices has chromatic number 5. And this started this polymath project. And so, but when Aubrey de Grey found it, he reached out to the media. Media reached out to Scott Aronson, back then a colleague at UT Austin. And Scott said, I have no clue how to check this result, but I'm pretty sure you can do it. And if it actually works, then with SAT, then you can probably do better. So that's what I then did in the weeks afterwards, is to use SAT to find smaller and smaller graphs that have chromatic number 5. So one of the challenges was actually okay, are 2 points distance 1, right? For example, there are 2 points shown on the slide. These are actually from one of my graphs. And how do you make sure that distance is exactly 1, right? And so what we use the Grubner basis tool, actually by Bieren, Kouwers, and Kaufman, to solve that problem, which can be expensive. And the other thing that we need to do is, if we have points in the plane, right, how do we make sure that it has chromatic number K? So one thing to do it is to ask the SAT solver to find the K coloring. And additionally, we also need to make sure that there is no K minus 1 coloring. So let me skip this. So how was I able to find these smaller graphs? So and this is the kind of a nice thing of SAT, is that if you ask the solver, okay, does it have, can you solve it with k-1 colors? And the answer is no. Then the solver can also produce a proof, so-called proof of unsatisfiability, showing that there is no four-coloring. And I developed all kind of techniques to really make proofs smaller and smaller. So I got some dubious honor of making the largest math proof ever, but the key thing is, of course, to make these proofs as small as possible. And I made all kind of techniques to make proofs small. And once you have a relatively small proof, then you can just look at all the vertices mentioned in the proof, and those vertices are also a k-chromatic graph. Right? Because if we didn't need any of the additional vertices to show that there's no k-1 coloring, and so you can simply solve the problem with k-1 colors, give it to SAT, give a proof, make the proof as small as possible, and then you only look at the vertices mentioned in the proof. Let me skip over this. This is kind of with proof minimization. So one of the things that, so these proof checking tools have been improved substantially, and actually even proofs that are petabytes in size can now be validated with formally verified checkers. I don't think it would be, is kind of, this is the place to really go into detail here, but you can, the proofs only take as very, only one rule, logic rule, and just many applications of them, and you can make verified checkers that go over these enormous files, and give a guarantee that everything is okay. The key thing how this works is that solvers, they learn a lot of facts, and at some point they learn, okay, the empty clause, or that there's no solution. And the key thing to actually make proof small is that actually you start with the empty clause, and then you kind of look, okay, what do I need? Which clause do I need to kind of justify the empty clause? And which clauses do I need to justify those clauses, and so on. And with all kind of heuristics, you can really kind of make the proof smaller and smaller. So in this case, the visualization shows the original formula and in blue, and then all the clauses learned in red, and the optimized proof in green, and then all the clauses that were used by the proof, so say the vertices for this problem, are then in the so-called core. And this visualization shows that the green part is smaller, but in practice, it's not uncommon that the green part is just 1% of the red part. Right, so you can really, using the right heuristics, and can you really make, so finding a proof is typically hard, right? But for once you have a proof, there's all kind of ways to make it smaller and smaller and smaller. Let me just not go too much over the technical content here, but you can do all kind of tricks to make proofs smaller and smaller. I won't go over it.
How do you your graphs, right? I mean, I understood your strategy.
Yeah. So I think that's the more interesting thing. So let me talk about the graphs, because I also think that the machine learning is able to maybe help here. So let's okay. So because if I have a big graph, right, I can use the proof minimization to get to a small one. But how do I get the big graph that actually has chromatic number 5 or even 6, right? So the key thing is to have this Minkowski sum, two given graphs. So, and the Minkowski sum is given as on the slide. And so if we have this graph with the 2 points over here and the 2 points over here, then the Minkowski sum is this graph shown over here. And so what we're going to do is two operations. We're going to do Minkowski sums and rotations. So the Moser spindle, which I also showed earlier, right? So if you have the graph shown over here and you have three colors, then the two opposite vertices always have the same color in every free coloring. Now, if you take two copies of it and then rotate one such that the points over here also get distance 1, then you can no longer have a free coloring because this one and this one needs to have the same color, this one and this one in the free coloring. But since they have now an edge between them, they cannot be both the same color. So this is the way we're going to construct things, and mostly Minkowski sums and a little bit of rotation. Now, the interesting thing is all these patterns that emerge in the fields with the square root of 3 and the square root of 11. So what I have here is HI is a 6 wheel with the edge length of length I. And so in this case, and we have also H prime I is the same thing, except that we rotate it by 90 degrees. And so if you have the graph over here, which is the Minkowski sum of H1/3, 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 it looks like this. And this is free colorable. But if we now do also with H prime, the square root of 3 plus the square root of 11 divided by 6. So this, you can move things around and this creates all kind of additional edges. Then the chromatic number is 4. And actually there's a lot of Moser spindles in here. And so this is already some kind of interesting graph, but it gets more interesting when we kind of continue to do this. So this was the result we had on the prior slides. And if we now do again the Minkowski sum with H prime, the square root of 3, square root of 11 divided by 6, then the graph looks like this. And so this is another 4 coloring. And the interesting thing is that most 4 colorings of this graph, the ones shown over here, they points that are close together, they have the same color. And so you kind of see this almost this hexagon tiling, which I showed you on one of the first slides, except that you use 4 colors instead of 7. And so somehow, of course, it's not possible to do all the points here, but use the pattern that actually the SAT solver gives you back is kind of almost a hexagon tiling, but just with 4 colors instead of 7. Now, if we do this again, and we do this graph with the Minkowski sum of H prime again, then we get the graph shown on the right. And the interesting thing, what you see here is that, okay, the patches are all gone, so that's no longer possible. But now what you see, I don't know how visible it is on there, but you see lines with the same color. And so almost all the solutions here, they have lines and points on the same vertical line have the same color. Of course, this graph is rotation by, you can 3-fold rotation or actually 6-fold, but so depending on how the solution is, you either have the lines like this or like this or like this. But there's all the solutions, they have the points on the same line have the same color. Of course, this is not, we cannot keep doing this, right? Because as soon as points have distance 1 on the same line, then that is not possible. But apparently on the same line, there are no points in this construction that have distance 1. And so this graph is a very clear pattern, and then you can keep doing this a couple of times by expanding it to a couple of Minkowski sums with H1 over H prime, and then you take away all of the points that are more than distance 2 from the center apart. And now you even see more clear all of the lines. Right? And so, yeah, so all of the solutions for kind of this graph, which has 2167 vertices, the solution, all of the four colorings have these lines in there. And now, so of course this is one thing. The other thing is here that all of the points at distance 2, so it's not completely clear where those are, but this is a point at distance 2. And also here, so all the points at distance 2 have the same color as the point inside in the center color. And now we can do the same trick that we did before with the spindle, is we take 2 copies and we now rotate it in such a way that points at distance 2 get an edge in between them, and then we have a 5-chromatic graph. So let's skip over it. But then, so this is 2 copies of the graph I just showed you. Then I rotate it such that you have points at distance 2 have an edge between them. And so that is a graph of 4,000 something vertices. And if I then use my proof minimization technique, I get a graph with 510 vertices. And that graph looks like this. It's also vertex critical. So any vertex, there's one vertex you can give color 5, and then but the interesting thing what you see here again is that, for example, this is the middle color is now white, is the only vertex with the 5th color. And you see again a little bit that points close together have the same color. So again, you see kind of something similar going on. So this is what I have been doing, right? So I have these graphs, find the right Minkowski sums, see these patterns, right? And I do now have tools to actually deal with graphs that have 1 million vertices. But now the question is, and maybe machine learning can help here, and maybe there might be good ideas here, is how do we make good graphs that either gets us even smaller ones for chromatic number 5, or actually be able to get to chromatic number 6? Because here I was able to get with a graph of, say, 4,000 vertices, get it down to 500 and change. But I am able now to deal with graphs with 1 million vertices. Can we find a graph with, say, 1 million vertices that has chromatic number 6? And then use the same techniques to kind of figure out what is a much smaller one. But I haven't been able to really figure out what are the right base graphs such that we can do this Minkowski sums that allow us to have a very kind of constrained graph, right? Because if you look also here, right, it's so the number of edges, it's extremely dense. And so one, of course, heuristic would be, okay, find ways that you get a lot of edges. But yeah, so I have now the technology to deal with 1 million vertices. The question is only, how can we find graphs that of 1 million vertices that have chromatic number 6? And so, of course, SAT cannot be really used here, right? Because I need to, so this is all kind of manually.
How long does it take to evaluate a candidate graph?
Typically, the issue is, in my experience, it always takes more time to figure out the edges than to figure out the chromatic number. So the SAT oftentimes is not.
Is that like days or minutes?
No, I think in a probably in a day you can do it. Yeah.
like a million graph or text graph you can do it in a day.
Yeah.
And it scales like n squared, I guess, so.
No, yeah. The scaling is, but so somehow the solver is really able to quickly figure it out, and figuring out the edges you can do probably closer. Yeah, you don't really need to n squared. You can, I think, closer to n log n.
Okay. I guess it could be kind of the pipeline where machine learning gives graphs and gets back results about a reasonable. Okay. Yeah.
So, and how to figure out what would be the good graph, because of course here it's just two graphs that I have, right? H 1/3 and h prime square root of 3 plus the square root of 11 divided by 6. And so these seem to be a really good combination. But yeah, can we figure out other graphs that are also a really good combination, and maybe a triple or even 4 different ones that somehow give you a really good so that the structure is enforced, and so the SAT technology is there to actually deal with even a million vertices and to really trim it to something small. The only thing that's for which everything I've been done so far is doing things manually, and I actually figured out these graphs by looking at some 5 chromatic graphs that I had and what kind of points were in there and how I could create them. So this is kind of how I figured out this, but since we don't have a chromatic number 6 graph, right, it's very difficult to figure out what might be a good candidate.
Okay, yeah, great. Now we can add this to our list of things. And you have a paper on the things you just described, right?
Yeah.
Great. Okay, cool.
Yeah, so I really love this problem, right? And it's, yeah, and this is, I think, where machine learning can really shine, right? Come up with something that is useful, right? This is not where any SAT technology can help to come up with the right base graphs, right?
So you mentioned there is what's the new technology to check again the distance 1 property? Is that some sort of Grubner basis techniques which you use? What's exactly that?
So that was more to, so what I mentioned here, right, of the Grubner basis was that in order to check that 2 points have exactly distance 1.
Yeah.
That's not cheap, right? And but what I'm doing here is that only when I find a 5 chromatic graph, then for all of the edges I do the expensive check. If I construct graphs just efficiently or quickly, then I just do a simple C tool that has integers distance up to 100 digits, and then round things up. And then only for the because if you would do this exactly, this becomes very expensive, right? Because you need to do it many millions of times. But you only have to do that when you think you have a nice graph that you want to be completely certain that all the edges that you have are exactly distance 1 and not because of a rounding error.
Maybe can you comment how Grubner base is coming? I'm just maybe a simple question I don't see.
I don't know the exact details, no. Yeah, so they have a paper on this, and I just use the tools. I haven't really looked into the details there. Any
questions?
Any other questions?
I guess not. Well, thanks.
Okay, great. Yeah, it was great talking with you, and I'm very interested in what ideas come out of these 2 months, and I'm happy to kind of follow up on the conversation.
Great, great. Okay, well, we'll definitely stay in touch.
Very good.
Yeah.
Okay, thank you all. Bye-bye.
Are we more to talk about, or we'll stop here for now?